today's video, we are going to solve problems regarding measurement, uncertainties, and propagation of errors. For our first problem, you measured the length of your computer table to be 45.72 centimeters using a wooden meter stick with an absolute uncertainty of plus minus 0.1 centimeters. A. What is the relative uncertainty of your measurement? B. What is the percent uncertainty of your measurement? And C. How are you going to report your measurement? We have given in this problem the measured length, which is 45.72 centimeters, with an uncertainty delta L equals to plus minus 0.1 centimeters. For letter A, we are required to solve for the relative error or relative uncertainty of our measurement. To solve for the fractional uncertainty or the relative error, we have this equation delta x divided by x, wherein the measured length is our x and the absolute uncertainty delta L as our delta x. Now let us solve for the fractional uncertainty or the relative error, absolute uncertainty of our length divided by the measured length. So we have 0.1 for our absolute uncertainty divided by 45.72 centimeters as our measured length. Our answer here is equal to 0.0022. Our fractional uncertainty or relative error is the ratio of your absolute uncertainty and your measured quantity, so it doesn't have any units. For letter B, we are going to solve for the percent uncertainty with the equation percentage uncertainty or error is equal to delta x divided by x multiplied by 100. So we have in our solution percent uncertainty is equals to delta L or our absolute uncertainty divided by the L or our measured length times 100. So we have equals to 0.1 divided by 45.72 times 100. And the answer is, of course, we got already the answer for our fractional uncertainty, 0.0022. So we multiply that by 100, we get 0.22% as our percentage uncertainty or percentage error. For letter C, our measurements are best reported with the reading plus minus the absolute uncertainty and of course the unit. So our reading here for the length of the table is 45.72 plus minus the absolute uncertainty of 0.1. Then the unit is centimeter. So here are our answers for this problem. For our next problem, we have 6 students measured the resistance of a lamp and obtained the following data: 661 ohms, 610 ohms, 658 ohms, 639 ohms, 645 ohms, and 628 ohms. Letter A, what is the fractional error of their data? B, what is the percent error of their data? C, how should the measurements be reported? We've learned from the previous problem that measurements are best reported with a reading plus minus the absolute uncertainty and the unit. But here in this problem, we have several repeated measurements. So for problems with several repeated measurements, we take the average plus minus the absolute uncertainty and of course the unit. So how do we get the average? So we have here the average is equal to the summation of our data divided by the number of trials or data that we have. For our absolute uncertainty or our delta x, we can solve that using this equation. Delta x is equals to range divided by 2. Our range refers to the difference of our maximum or our largest measured value minus the smallest measured value or our x minimum, then divide it by 2. So it is important that we solve first for the average of our data and our absolute uncertainty before we can answer questions A and B. So here we have for the average of our data, we take all the data or the measurement. So we have 610 plus 658 plus 639 plus 661 plus 645 plus 628. Then we divide it with the number of data or samples that we have. So we have 1, 2, 3, 4, 5, 6 gathered data. So the answer here is 640.17. Next, we solve for the delta x using the equation range divided by 2. So we have the largest value is 661 minus the smallest value. So we have 610 divided by 2. So the answer here is 25.5. So here we round off our answers to 640 plus minus 26. Now we can proceed to solving for the fractional error of their data. So for letter A, we have the equation for fractional error or fractional uncertainty equal to delta x divided by x. So we have our absolute uncertainty is plus minus 26 divided by 640. So we have equals to 0.04. For letter B, with percent uncertainty, delta x divided by x times 100. 26 divided by 640 times 100 is equal to 4%. So for letter C, we have our measurement is reported as 640 plus minus 26. Of course, the unit is in ohms. In our next problem, in measuring the angle of refraction at an air glass interface for a constant angle of incidence, the following results were obtained using a protractor with a precision of plus minus 1 degree. We have 45 degrees, 47 degrees, 46 degrees, 45 degrees, and 44 degrees. How should we express the angle of refraction? From our previous examples, we have measurement for several repeated measurements is equal to the average plus minus absolute uncertainty, and of course the unit. So we first solve for the average of our data, and then we solve for the absolute uncertainty. So let's take first the average of our data. We have 45 degrees plus 47 plus 46 plus 45 plus 44, and then we divide it with the number of data that we have divided by 5, and the answer is 45.4 degrees. Next, we solve for our absolute uncertainty. Delta x is equals to 47 minus 44 divided by 2. Our absolute uncertainty is equal to 1.5 degree. Here we are going to round off our answers to 45 degrees plus minus 2 degrees. So our final answer is 45 plus minus 2 degrees. For our next problem, here we are going to propagate the errors that we have or obtain in our measurements. A car travels 64.7 plus minus 0.5 meters in 8.65 plus minus 0.05 seconds. What is its speed? So we have the given distance traveled by the car, 64.7, with an uncertainty of 0.5 meters. And then the time is equals to 8.65 with uncertainty plus minus 0.05 seconds. Here we are required to solve for the speed of the car, considering that it has uncertainties in its measurement. So first solve for the speed of the car using the equation speed is equals to distance divided by time. So again, our measurement is best reported if we have our reading plus minus the absolute uncertainty and the unit. So for our solution, we have speed is equals to 64.7 meters divided by 8.65 seconds, and the answer here is 7.48 meters per second. Now in propagating errors, if data are to be multiplied or divided, we add the fractional or percentage uncertainty. So we recall that fractional uncertainty or the relative error is equal to delta x divided by x. In our case, so we have our speed, delta S divided by S, is equal to the sum of the fractional uncertainties of our data. Absolute uncertainty for d, delta d, divided by distance, plus absolute uncertainty for time, delta t, divided by time. Since we have a given measurement for speed, which is equals to 7.48 meters per second, we substitute our values. So we have delta S divided by 7.48 meters per second equal to 0.5, the absolute uncertainty for distance, divided by measured distance, 64.7, plus the fractional uncertainty of time, 0.05, divided by 8.65. If we multiply both sides with 7.48 meters per second, so we have delta S is equal to 7.48 multiplied by the sum of our fractional uncertainty, which is 0.0135. So our delta S, or our absolute uncertainty for speed, is equals to 0.10. So we report the speed of the car as 7.48 plus minus 0.1 meters per second. For our last problem, a cylinder has a radius of 1.60 plus minus 0.01 centimeter and a height of 11.5 plus minus 0.1 centimeter. Find the volume of our cylinder. Of course, with a given uncertainty, we solve for the volume of a cylinder using the equation volume is equals to pi times square of our radius times the height. So we plug that into our solution. Volume is equals to 3.14 times 1.60 centimeter squared times 11.5 centimeter. So we get the answer 92.44 cubic centimeter. So here we have a given uncertainties. Again, if data are to be multiplied or divided, we add the fractional or percentage uncertainty. Our absolute uncertainty for the volume can be calculated using the equation fractional uncertainty of our volume is equals to fractional uncertainty of radius, delta r divided by r, plus another fractional uncertainty for our radius, because in our equation we have to take the square of our radius, delta r divided by r, plus the fractional uncertainty of our height, plus delta h divided by h. We can simplify our equation to 2 times the fractional uncertainty of our radius, delta r divided by r, plus the fractional uncertainty of our height, delta h divided by h. So we have 2 times 0.00625 plus 0.00870. So fractional uncertainty of our data is equals to delta v divided by v is equals to 0.0212. So in order for us to get the absolute uncertainty of our volume, we may multiply both sides with our measured volume, 92.44. So we are left with the absolute uncertainty. So absolute uncertainty is equal to 92.44 multiplied by the sum of our fractional uncertainties, 0.0212. So the answer is 1.96. We round off our uncertainty to one significant digit, so our volume for our cylinder with uncertainty is equal to 92 plus minus 2 centimeter cube. That's it for our video. I hope you have learned something.